Our next speaker is Nguyen, also one of our own. So Tree was here, IAIFI, graduated from MIT a year ago, more or less now. He is right now a postdoctoral fellow at Northwestern, part of the Sky Institute. And he's been doing a lot of work on trying to understand the nature of dark matter with Gaia data, but also working at this intersection between compute and simulations and machine learning. So you're really excited to hear what Tree has to tell us. Thank you.
Yes, you will all see the jellyfish with always. All right. Hi, everyone. Thank Carol for the introductions. Excited to be back. So I want to tell you today about galaxy formation and specifically an application of machine learning into the field of galaxy formation that I have been very interested in recently. Even though, disclaimer, there's so many ways that you can use machine learning for galaxy formation. What I'm about to tell you is a very small subset of it. All right, so let's get started. So as with all astrophysics talk, I want to start with talking about galaxies, dark matter, all the components of galaxy formation, and especially start with the very beautiful pictures. So this is the pictures of the JWST deep field. In this picture, you can see many galaxies. But if you ask a lot of people what are the galaxies that are most interesting in these pictures, a lot of them will tell you that these are all like the red galaxies. And the reason, so this is from JWST. The reason for the red galaxies is that they're usually typically more farther away. As you know, the universe is expanding, so everything's kind of like moving away from you, so it's Press-Schechted. Also, can depend on the properties of the galaxies a little bit too. So JWST launched, I don't really remember when it's launched anymore, it's been a while. But it's one of like the NASA flagship mission, and it's very powerful. Oh, sorry, I forgot about that.
Oh, yes, I did.
Yeah.
What would you like to know? Sorry.
Hello. Okay. Okay. Yeah, is it good? Yeah. Nice. Okay, sorry about that. I hope my voice was loud enough. But yeah, JWST can see much farther and much fainter population of galaxies than the predecessor, which is the Hubble Space Telescope. For example, if you see here, there's this column here, a little bit difficult to see with the light in, but this is the same photos for Hubble and the same photo for JWST. And here you can obviously see that Hubble is kind of like missing a lot of the galaxies that is usually more redder, which is usually more farther away than JWST. And JWST revolutionized the galaxy formation field by also kind of like, in a way, throwing a wrench in it. So it has revealed populations of galaxies that is much more massive and more abundant than expected. Here, for example, you can see if you can like calculate the amount of like mass in the universe, mass of galaxies, then JWST you can kind of infer from just like the number of galaxies, how massive they are, at what volume of the universe, the kind of like, like how much mass there is. And it's kind of like reaching the limit where it's almost like violate lambda CDM. And another example is just like cumulative count functions where you have number of redshift versus like normalized cumulative count. And like all the curve here, so the shaded is JWST observations. All the curve here are different kind of theories. So we have cosmological simulations, we have all the kind of like semi-analytic, semi-empirical models, and all of them kind of like predict the number of galaxies much lower than what you expected from, than what you see from JWST. So what's the common way? So how do you actually come up with this theory? How do you kind of like improve this theory so that it matches the observations a little bit better? So a very standard way of studying galaxy is by simulations and by semi-analytic models and all of that. But first, I want to just give you a kind of like a quick pictures of galaxy formations. So if you're not familiar, the universe is made up of, let's say, 85% of dark matter. We don't really know what it is. We have evidence that it exists. And all galaxies are embedded in this roughly spherical regions called the dark matter halos. So let's say this is the galaxies, very cute disky galaxy here. What actually happened is that you have the galaxy here, you have a dark matter halo, not really to scale, that extend like much, much beyond the kind of like the quote-unquote observable boundaries of the galaxies. And you have a bunch of dark matter subhalos, which is like the substructure of this dark matter halo. It's not completely smooth. So basically, to want to model galaxy, you have to kind of like model the dark matter halos a little bit too. And one of the reasons is that in the early universe, you don't really have galaxies. All you have are halos. So all these halos start small. They will merge with each other. They will start to build a building block. They become a building block of the universe. So eventually, when a halo is big enough, you will have galaxies, and then they will keep merging and merging with each other until you see the galaxy population in the present days. So to understand the galaxies, we need to understand how the halo merges with each other. So let me give you a quick example, where here is the early universe from the top of the panel to the present day. Let's say you start with some kind of population of dark matter halos. There's no galaxy in it, very, very tiny dark matter halos. Eventually, some of them will merge with each other, and maybe they will pop up the galaxies in when they are massive enough. Sometimes they just kind of evolve, and how they create galaxies, whether or not they will have galaxies, kind of just depending on the environment of the dark matter halos. And they will keep merging until they form the galaxy that you see in present days. And this is a very simplified pictures of the hierarchical galaxy formation process. But it's like roughly describe how we usually model galaxy formation in modern galaxy formation theory. And this is what you call a merger tree, because it's kind of look like a tree structure. So to model galaxies, what we usually do, just so you can run simulations, cosmological simulations, starting from like the very early universe, and evolve the entire cosmological simulation box to present days. That can be extremely expensive if you want to model all the galaxy formation physics to it. So what people commonly do is they would run a dark matter only simulations, which can ignore all the baryonic physics. So similar to cosmological simulation, but just no stars, no galaxies, no anything. So just dark matter halos merge with each other, and then they find a way to paint the galaxy, to assign the galaxy properties onto each of those dark matter halos based on some kind of baryonic prescription, like galaxy formation physics. So there's many ways to do that. One of the way is semi-analytic models. So they basically take this dark matter merger trees here. So there's only dark matter halos here. They would add on some kind of simplified baryonic physics, so like stellar feedback, galaxy formation, like gas cooling, how gas get accrete into galaxies, and if you want to, you can also model dynamical process like tidal effect and all that. And then you will get the galaxy merger trees. And this can be very, very fast. You usually only need to run the n-body simulation once or twice. And then you can explore the parameter space of the galaxy formation physics if you want to. And what I want to focus on today is this component. So I did make a comment that you really only need to run it once, but it really depends on your application. Sometimes you need more merger trees, and then even then, n-body simulation can be expensive. So how do people typically generate this kind of merger trees beyond simulations themselves? So let's two common ways that people do this. So one, like I say, you can use n-body dark matter only simulations. You have run some kind of cosmological simulation box, and you have ways that you can compress all these densities into an actual merger tree structure. And the second way that you can do this is with analytical models with the extended Press-Schechter formalism. So what people typically do is, one of the most important properties of a halo is the mass, right? So the extended Press-Schechter, what it does is that it gives you the conditional mass function. So let's say if I have the Milky Way at present day with this mass, what is the likely progenitors of the Milky Way at some kind of time in the past, and what's the probability density distribution of that mass, right? So it gives you this, but to construct the merger tree, you have to make a bunch of assumptions to actually construct this, and some of these assumptions are a little bit ad hoc, and at the same time, the conditional mass function itself, if you're familiar with galaxy formation, it neglects a very important component of this evolution, is that the environment of the galaxy, it doesn't account for any of that, right? And so that as a result, if you take a look at the sphere, and I'm showing here the halo mass as a function of the time. So this is present day, this is the early universe. So it's kind of like evolving from left, like evolving from right to left, but people typically show it from left to right like this. And so basically here, all the gray is like an example of like kind of like a halo with a halo mass of one halo versus like the redshift for this like that's generated by this standard Press-Schechter analytical models. And each of these panels is just different methods. And all the red ones are like all the red lines are like the one that you actually get from cosmological simulations. And you can see that there's the discrepancy. Like for all of these methods, there's a discrepancy. And some does a little bit better than the others. But the common trend is that they would kind of typically agree with simulations at very, very low redshift, or like very like at present days. And then in the early universe, they will start to like deviate very significantly from each other. And I want to show this too, because Parkinson et al. 2008, this is a very old field, is one of the most common and kind of like industry standard in galaxy formation when you deal with this kind of extended Press-Schechter generative models. So can you do better than this kind of analytical models? So can you use machine learning to do this? And I guess the answer is obvious. If not, I would not be here and talk to you about this. So yes, you can. But let me go a little bit in depth about this more. So what is a merger tree? So merger trees are basically a very, very special graph, right? Like you can model it as a directed graph, with let's say this is early universe. Sorry, this is present day. This is early universe. You start with like the so-called root halos. Which, let's say this is the Milky Way. This is the Milky Way in the past. So each of these nodes represented a halo, right? And the snap here is like the simulation snapshot. So kind of like a snapshot of the time in the cosmological simulations. And the red branch, I just want to denote it because people typically attribute some importance to it. It's the main progenitor branch. It's basically what happens if you just go down the street, you keep following the most massive halo at all times. And like I say, the mass is one of the key properties of the halos. So it's one of the, or if not the most important properties. So you can represent merger tree as graph, and you can try to use some graph generative models to it. But a few things that you need to keep in mind when you're dealing with this kind of tree structure. So one, just for everyone's on the same board. In galaxy formation, we are weird. We use the word history very weirdly, because typically when people generate this merger tree and people use all these terminologies, we go in from present day to the past, like present to early universe. So by that terminologies, a descendant halo is like this halo, and like if it was evolved from a halo here, then this halo is called a progenitor halos. And the progenitor has a very unique evolution history. So basically what it means here is that when the halo merge to each other, they do not split again. Like in reality, they could physically or just numerically from the simulations, but for all intents and purposes, like every single time that happens, usually it's numerical noise. So you don't really want to model that. So yeah, so basically, like let's say for example, if this halo, and in the terminology that we were like talking from like present day to early universe, if this halo split into this halo, they do not combine again. Like loop does not happen in this kind of graph structure, and you want to really, really respect that, right? And the second thing is like both the number of progenitors. So at every snapshot, the number of progenitors and the properties of the progenitors you can somewhat treat it as like a stochastic process. And especially when you model everything from like present day to early universe too. And the reason I put the stars to it is that if you have access to like the initial condition of the universe, then it's not really a stochastic process. But for intents of purpose, we kind of treat it as stochastic here. So can you just like use like normal graph to it? So before, actually, I want to show you, this is an actual example of a merge tree. This is one of the bigger one. But this tree is like gigantic, right? And to model this, you need to actually model all these connections correctly. You need to make sure that there's like no loop, no random loop in these trees. So it's not exactly a simple task. The good news is that not all of the halo is important. So like if the halo has too low of a mass, you don't really care about it. So let's say I just use like a graph neural network to this. Let's say I use a graph VAE, a graph like normalizing flow, or even use diffusion models to do this. So can I do this? So typically, if you're not familiar with graph theory, let's say this is a computational graph, you can kind of represent it as something called the adjacency matrix. And with the merger trees, you can kind of like assemble this adjacency matrix, and you can order in all this node in a way that make it a little bit more organized than this. But let's say if I want to use a graph generative models, then what I could target, for example, is that I could target this adjacency matrix directly, right? But when we tried this, we found a couple of problems with this approach. So one is that some of these models, not all of them, for example, graph NF, requires you to know the number of nodes beforehand. Some models would just learn the distribution of the number of nodes and just kind of generate it on the fly too. But some of these models require you to know the number of nodes, and this is tricky for merger trees because the entire thing is stochastic. The number of nodes is stochastic, and it really also depends on like the root mass or like of the halos and all that. So it's not, and in why you can really model it, it's not really the distribution of, say, n versus like root mass. It's not very ideal to do so. And like I said before, there is a restriction on what kind of graph structure that you want to generate. So you can never actually completely prevent loop in this. Like you can probably get like okay result if you have like enough training data, so that your model just learn that there's no loop around, but you can't entirely prevent it. And you can technically process it out, but that introduces some ambiguity, right? So let's say, for example, if there's a halo that's split into two halos and then these two halos combined, if I'm going to process this, do I remove this edge or do I remove this edge, right? So there's some ambiguity into this process. Another way that people have done with graph generative models is they can use autoregressive models. So this is an example of an autoregressive model called graph RNN. This is designed for any kind of graph structure. So it's not specialized for tree yet, but it has some potential. And the way that people do it is that they would kind of like starting from an empty graph, and they would generate one node at a time, right? So they have the starting token, they generate one node, and they generate some kind of edge. And they can add another node to it, and they have like another models to see like whether or not this edge should be connected to each other, and they can keep doing this, right, until you have like a full graph. And you can see here that it doesn't really have any kind of restriction on what kind of connection it could have. But what if we modify it a little bit to make sure that we can like model a tree structure? So let's say, for example, you look at this very simple trees here, right? You have the root halos here. And the root halos, you can, for intents and purposes, you can always assume that it's given to you. And basically, it's the mass, dark matter concentration, all these kind of properties, physics properties that you want, as well as the time, the root halos. And you can also assume that you will have like, a list of time that you want to like model the merger trees at. So basically, given this root halo and only this root halo, you want to generate this entire trees. And let's say we want to generate it autoregressively, which means that I would go from snapshot 3, I would generate snapshot 3, now I would generate snapshot 2, then it would generate snapshot 1 and snapshot 0. And now let's say you consider one of a random halo here, right? Let's say this star halo is snapshot 1. Then really the only two questions that you want to ask yourself, or you want to ask this halo, is that given, you know, like all the previous information that you can give this halo, so cosmological information, the halo evolution, quote-unquote history, what is the number of progenitors that it will give you, and what is the properties of those progenitors? If you know those two numbers, I think you can model the entire, you can model this part. And you can auto-recursively keep, you know, like model it until you model a completely full merger trees, right? So in a kind of way, you can just write your distribution as like some kind of like number, like a joint distribution of the number of progenitors and the progenitor properties. And you have to do it for every single halo. Yeah, so we have this framework called FLORAH. So let's say we start with the descendants and the history. So the descendants is this halo. The history is all the orange halo or the red-orange halo that I'm showing here. And you want to output the number of progenitors. You want to output the properties of those progenitors. And let's say you just do it deterministically for now, right? One thing you can do is you can just have in like a transformer. You literally just put it in the transformer. So the input is a time series. You put it to a transformer encoder. It's going to embed some kind of history. So to predict, you know, number of progenitors, you can like feed that encoding and like embedded latent space to some kind of classifier. It can output you n, and you can feed this into a decoder, and it's output you another series, and that can be the properties of the progenitors. So if you want to make it random, all you need to do is make sure that this process, like this is random and this is random. So basically what we do here is we have like the training process. We use this as it's like cross entropy loss. So this classifier just predict you like a vectors of probabilities. And so here we basically make the assumption that this process is like multinomial with some kind of P that predicted by the classifier. So you just use cross entropy loss for this. Of course, if the number of n is more complicated, you can do some other things too, but this is what we choose for this model. And you can have some kind of reconstruction loss here, NLL loss here to make sure that the properties match with the previous properties. And the way you train it is just that you can just literally go node by node. So like take all the node in this tree, for example, you can like do the forward models for like each of these nodes and then combine their loss function. That's what we did. One thing that we also found important is that the number of progenitor is important for the decoder process. So basically to predict the properties well, the decoder models also need to kind of like know the number of split, which makes sense if you think about it in terms of like mass conservation, for example. So just the decoder, a little bit like how we model it here. So for simplicity, we arrange all the halos from the most massive halos, second most massive, to the least massive halos. And let's say you have a list of n halos. Here I'm only showing you 3. So what we did is that we just start with a starting token. We have the properties of the first halo, properties of a second halo. What we did was that we just generate them also kind of like auto-recursively, like this. So let's say, for example, during generation, you have the starting token. You feed to the transformer decoder with some kind of encoded features or any conditioning that you want, and that kind of like just predicts, like, and then we feed that features into, let's say, a normalizing flows or any kind of like NDE would probably work. Then you can sample it, and then you can feed it back, and then just do this entire process again. There's multiple ways you can model like a series like this, but this is just the way that we end up with. And then like during training to calculate the loss, all you do is just take the flow and you just evaluate the NLL loss of the flows. Yeah, so does it actually work? So this is some example of some of the generated merger trees. So each of these columns are just different mass bin for where the mass is the root mass. This is started with a 10 to the 13 solar mass at present day. It's roughly 10 to the 12 solar mass is present day, 10 to 11, and 10 to the 10. As you can see, like all these trees have very kind of like diverse structure. Like if the mass is too small, sometimes you would expect nothing to like merge with each other, so there would be no split. It's just be a straight line, very boring tree like this. And if the mass is very massive, then you can see that they can split like a lot and create a very, very complicated graph structure. And I actually pruned this tree a little bit. I removed some of the halo with too low mass so that it can look like this. But in reality, the tree can be much, much more complex than this. But you can do better than just basically just plot a bunch of these and just cleanse enough of them to see if they actually match with the simulations. You can calculate things like halo merger statistic. For example, here we compare a bunch of halo mass function. For different color is just different snapshot, different redshift, different time in the universe, where the solid line is the generative models that we have, and the shaded region is the simulations that we have. And this is just the cumulative number of halos as the mass. So like these are some of the more common, summary statistics that like cosmologists or like galaxy formation astrophysicists would take a look when they want to cross-check these merger trees. You can do a little bit better. So you can plot things like the merger rate, which is basically count the number of halos that merge to each other and kind of like plot them as like their mass ratio. So the x-axis is the mass ratio. And different color here is just different bin of the mass of the descendant halo. And to the left, you see our methods versus the simulations, where the data point of the simulations, our method point, and our method is the solid lines. And the bottom panel showing the residual. This is with the standard Press-Schechter or like the analytical models, the kind of like industry standard that people usually use. And here it doesn't look very, very bad, right? Because it's like the present day. So everything lines up very, very nicely. But like I said, the problem with Press-Schechter is that it will kind of agree with the simulations at early redshift, and at high redshift, everything starts to go off the rail. And in this particular case, it have a tendency to kind of like over-predict the merger rate. So this you can kind of see here. And one thing I want to also comment on is that if you look at this mass function, right, the mass function has a tail towards like the right, like to the massive n. So meaning that there's a much, much fewer massive halo, like exponentially fewer massive halo than low mass halo. So you want to really capture the population of massive halo very well too, as well as the population of low mass halo. And so when this is like different mass range, so you can kind of see that we can, in a way, be able to like do that. And also at the same time, the problem usually with auto-recursive model is that if you don't train it very nicely, that any error that you have at the earlier stage, it will accumulate and into like the latest stage. Which can be really bad, but you don't really see it here. So between this and this, there's like roughly 20, 40 step of the autoregressive models. And the last kind of result that I want to show you is is how you can actually, one of the way that you can actually use it. So yeah, sure, so you can get dark matter halo very well, but that's not really your end game. Your end game is really this galaxy merger trees. So, and if, even if all these summary statistics I'm showing you agree, if for some reason I predict different galaxies' properties than the merger trees that I extracted from n-body simulations, that's not good. That's actually really bad. So you want to also apply the galaxy formation, the semi-analytic galaxy formation models that you would normally apply to kind of like solve physics problems. To this and to see if the properties match. So that's one of the things that we do. We use this model called Santa Cruz SAM. We apply it on all the generated merger trees, and we're trying to compare it with the simulations. So this is an example. So this shown here, the stellar halo mass relation. So what is the stellar mass versus the halo mass? And all the bands just showing the median and the 68, the 1 sigma band. With the orange color is our method, and the blue color here is like the simulations. And here we're doing the same, the bottom panel. But instead we compare the extended Press-Schechter based tree with very small MultiDark, which is the simulations. And here I'm showing this stellar halo mass relation, scatter concentration relation. So this is an important relation to get, and you can see that extended Press-Schechter kind of doing like very, very well, kind of like down to like very low halo mass. But this is this is more tricky to get. So what this actually show you is it show you like the scatter of this figure versus like the dark matter concentration. And effectively, what it show you that there is some kind of dependencies on the stellar mass of the galaxies that is not other than the halo mass. And in galaxy formation, we call it galaxy assembly bias. So this is kind of like roughly model the effect of like the environment, for example, on the evolution of the stellar mass. And here, this is one of the, if you remember, at the start of the talk, I said that extended Press-Schechter doesn't capture the environments very well. This is an example because it just returns you a flat line here, while like if you actually model it properly with the cosmological simulation, in the case here, or generative models, you can actually get some kind of relations. So we can do something that extended Press-Schechter cannot do. And if you really into galaxy formation, I want to flash this figure showing supermassive black hole mass versus halo mass relation, because this is like all the cool kids are doing now. They're doing like supermassive black hole modeling for high redshift universe. So you want to really get the supermassive black hole mass right. And one thing about supermassive black hole is that all the theory on the evolution of supermassive black hole is very heavily related to like mergers. So basically, whenever there is a mergers, it will kind of like speed up the black hole. And it will make the black hole accretive faster. So if you get the merger rate wrong, any kind of properties of the halo mass wrong, the supermassive black holes relation will get really messed up. So here, because extended Press-Schechter, what they do is they overestimate the merger rate. So you see that the supermassive black hole mass is more massive than usual. All right, so I want to end the talk with just kind of looking forward in the future. So what can you do with this kind of models? So here's a typical framework in galaxy formations. You start with some kind of like simulations. You generate a light cones, which kind of like almost like emulating your observational effect. And then you generate some merger trees, and you want to, like this entire part, just like predicting galaxy properties, and that started by generating merger trees, apply the semi-analytic models onto the merger trees to predict the galaxy properties, and assemble them into a catalog. And you don't really have to worry about like any part of this. This is like for the astrophysicists to care about. So what you can do is you can just like replace the extended Press-Schechter with merger trees. And the reason that you cannot just like keep running n-body simulations to get like better merger trees than analytically generate them is that if you typically look at like a way that people generate the light cones, it includes like a tons of halo. This is like a lot of dark matter halos, and you want to generate a merger trees for each of them. If you're running n-body simulations, you will eventually run out of halos, or you will not be able to like match them properly, which is also annoying. But basically with some kind of like generative model, analytical models, you can generate much more merger trees, and using the merger trees, you can properly populate the light cones here with the galaxies, and you can create a galaxy catalog, and you can take the galaxy catalog, you can go to the observer at JWST, and you can compare the properties and see if your theory is correct. Another way that you can do this is by modeling galaxy satellite system. So this is actually closer to the kind of science that I do. I love small scale stuff, so like Milky Way, satellite of the Milky Way things. And Milky Way also form hierarchically like any other galaxies. And all the halos that merge into the Milky Way become the subhalos or the satellites. So for example, large Magellanic Cloud, small Magellanic Cloud, if you ever see them or heard of them, then they are satellite galaxies of the Milky Way. And the way that they orbit the Milky Way, very dependent on, as well as other dwarf galaxies too, is very dependent on the properties of the hierarchical merger. So the merger trees of the Milky Way is all depending on the kind of formation, the galaxy formation physics, the kind of dark matter models that you were looking at as well. So you can use the properties of satellite to prop fundamental dark matter physics. And you can actually do it better than some cosmological survey can do. So one way is to take the merger trees, and you would have a semi-analytic models, but instead of modeling galaxy, you would model in satellite instead. And this is an example from this semi-analytic model called SatChain, which is the one that I also used for the merger trees, for the extended Press-Schechter merger trees generation previously. So So all of the properties, like I say, really dependent on the kind of physics that you have. For example, if you have like cold dark matter, you will have like way more substructure than if you have something like warm dark matter, or just any kind of like different dark matter models, any kind that you can name, probably give you a slightly different pictures of this. So if you don't model the merger trees of the Milky Way correctly, you will not be able to model these correctly. And that would give you like some errors in your kind of like theory observation comparison. And at the same time, when people do this kind of satellite system modeling comparison, they also typically don't really do like with like variant dark matter models. But I digress a little bit. I really like dark matter. And one of another interesting, the last application that I was really excited about too, is that, so everything that I'm showing you was kind of like within the boundaries of the simulations. So what if you can somehow go beyond the simulations, right? So simulations embody like hydro simulations, they all have the same problems. It's called the mass volume tensions. So basically when you run the simulation, you have a volume with a finite amount of mass. And what the people do is they will generate particles out of that mass. And the complexities of their simulation will scale with that particles. It's not exactly n squared. Scaling law is very complicated, but it's kind of like n log n plus like n something plus some kind of additional parameters. So you can't really have a simulation with high mass and high volume. What do I mean is that if you have a very small mass simulations with high resolutions, you can really only capture galaxies up to a certain amount of mass. If you have a very high volume simulations like this, you can, or like high mass simulations like this, you can, but like low resolution simulations, you can capture like more massive galaxies or like galaxy cluster, but you can't really see the smaller guy. If you're trying to have both, then your amount of money in computational time, which is related to money, I guess the other way around, is scaled exponentially, and you can't really do anything about this. So a way that we were thinking is that let's say you have a very low volume, high resolution simulations, you can maybe combine it with a medium volume, medium resolution simulations as long as there's some kind of overlapping between the simulations. And you can do very high volume, low resolution simulations. And you can find a way, if you can like extrapolate or like between these simulations to kind of like combine them into one that has both high volume and high resolution And one way that we were thinking about doing that is we can just like take all the simulations, we can just combine them into one big data set and train the models on that data set and see how it works. So example here, I show you the cumulative mass function. So halo mass has the function, just the count of the halo mass. And the simulation I'm showing here are like these graph simulation, graph 5, graph 15, graph 35, and 90. So they all have some kind of overlapping between this halo mass function. So this is what I mean by complementary simulations, right? So the graph 5 has like the highest resolution but lowest volume, and this has the highest volume but lowest resolutions. And what if you combine them into like one big training data set? Can you actually extrapolate between the capabilities of the simulations? So I'm showing here is the mass versus redshift. And the dot lines or the dashed line are the simulations. This is the mass assembly history that you get from the simulations. And the curve, the solid curve is what we got if we train every models on this combined set of simulations. And what happened here is that you can see the mass of the halo, they would go down, right? Like at the early universe, the halo gets smaller, but then they start to disappear. And this is because you start losing, like with not enough resolution, your simulations at high redshift start to actually become wrong. They predict the wrong populations because they lose halo. They lose the small mass halo. You can see this kind of like flatten out like this. And the orange line is the simulation with some overlapping mass range here, but it has like higher resolutions. So it keeps going down, right? So this is purely a numerical effect. And what I'm showing here that if you train the models that combine all these 4 simulations, you can actually go much, much lower to this. And this is very interesting because it means that you can effectively, if you combine the right simulation, simulate a galaxy cluster up to extremely high redshift, which is nobody have ever been able to do. And to end, I will have just put on my main takeaway slide, and I will answer any question.
Thank you, Trey. We have a few minutes for questions.
So if I had to simulate this for so where in your architecture would I feed in information about the power spectrum? Because if I had to reconstruct trees for a modified, like let's say an enhanced or a suppressed power spectrum, how would I go about doing that, or would I just have to retrain from scratch?
You need to retrain. So this is still like the current model, right? Like I'm still emulating what's in your like within the n-body simulations. If you have a suppressed power spectrum, let's say one dark matter, you need to find appropriate simulations for that.
I think usually in this case, people define like a universal time, which in merger trees, which can stay invariant across different cosmologies or in different power spectrums, which just depends on the integral of the power spectrum and like the barrier that we use in extended Press-Schechter. So can something like this, if you create a tree with respect to this universal time instead of like actual time, can we use that to just quickly simulate for modified power spectrums instead of having to retrain? So
I'm not 100% sure what you're asking, but if I understand correctly, you're asking if I can just kind of like in a way condition these generative models on the properties of the power spectrum that you have?
Maybe I can come talk to you later, but
yeah.
I can explain. Okay, yeah. Okay, thanks.
Okay.
Thanks for the nice talk. I wanted to ask about like the comparison from EPS, the extended Press-Schechter. I mean, there have been some models where you can have like this power laws or redshift dependence to be like fitted by some coefficients. I mean, those have been, like you can make it more accurate than EPS, but it still uses like the mass as the only parameter for the merger history. So like, did you also compare with that?
So this model actually did that. This model, so what they do is they would generate a mass assembly history first, and they would use the mass assembly history to calculate the concentration. So that's one way that people have used to get around with that. I think there are like more updated models out there, but I'm not entirely sure on the extended Press-Schechter kind of like literature. I mean, there's still a fundamental problem with extended Press-Schechter is that when you're trying to generate that, because the way you have to make some ad hoc assumption on whether to obey mass conservation or obeying the conditional mass function. I don't think there's any way that you can get around that.
My question was just like more the comparison of your model to some flexible analytic models, let's say, like this entire machine learning model to some flexible analytic models.
You mean so like a different model or something?
Like a flexible analytic model, like some extension of Press-Schechter. Maybe I can talk to you later.
Yeah, this is like the one that I'm showing you is kind of like the updated version of extended Press-Schechter. So it does take into account a lot of like environmental effect. Yeah.
Hi. Again, as everyone else said, thank you for the very interesting talk. I was curious about, so I'm not overly knowledgeable about dark matter subhalos, but it seems like based on the autoregressive model you're using that you're only really looking at like the most recent kind of subhalo when like looking at the properties of like, when predicting the properties of like the future ones or how many the future ones are. Have there been like studies done where they're maybe considering like previous nodes like further down the tree and their impact like on the next predicted models or something like an LSTM or like something like that?
So so in this model, I actually I don't like so generate this. I don't just consider this. I consider this.
Oh, okay. Sorry, I misunderstood then. My bad.
So that's also like a better like the way that like extended Press-Schechter fail is that it's only considered this, and we consider every single
okay, I see.
like every single node.
Right, that makes sense. My bad.
Yeah.
Other questions?
Thank you for the nice talk. I have a dumb question. I apologize in advance. But have you tried to use ChatGPT to generate your merger trees? The reason I ask, I would have said it's dumb, is that some people were able to generate very nice looking materials, proteins and such, and crystals. by fine-tuning through the OpenAI fine-tuning API. So I was just curious if you tried it and it might work by accident.
I have not, but ChatGPT did help write part of the code. With human supervision, of course. But I guess my worry with doing that is that it feels like it's kind of like roughly going the same way, which is using like VAE, or just like some graph-based generative model, is that you can't really avoid it to like generate the loop, which is like because you need the merger trees to obey that kind of structure, and I'm not sure if it can generate a tree without loop. Yeah, but that's just my worry. But maybe I'll just put it in after this.
I have a question as well, Tree, on why did you decide to go backwards, right? Because it seems like the problem of going forwards is much simpler. It's deterministic, right? Yeah. You have more information of what's around you, so you know what can actually merge into you. So why do you decide to go backwards instead of forwards?
So one is that it is a convention that people use in galaxy formation. I have been thinking about trying to make it like go forward, but I guess like to make it go forward, like I guess it's just like a different way of models thing together. Like you would generate a bunch of halo at the end, and you will see which halo merge into which. But the problem is like you don't really know the number of halos at like high redshift, right? And sometimes they do like sometimes if you want to take into account the resolution effect, sometimes the halo do just like pop up randomly. Like what I mean is that if you like look at like this tree, right? Like not all of this, like let's say this, like it started with like one halos, but like if the halo reached the resolution limit, then you know it's kind of like just pop up or like it's get captured by the simulations. So now for example, it has like one halo here, but it has like two halos here, right? And it has like n number of halos here. So one is like how do you capture that? And like even if you have like a list of entire halo here, like this depends on number of branch. So like how do you sample it in the first place, right? And also, it's more useful to go backward in time because what people do is that people would give you, because of the way the data have, right? So like you would be given this halo. Like you are not given this halo, you are given this halo, right? And even if you're not given this halo, you can make a very strong assumption of what this halo should be. So you're always given the halo at present times, right? So it's better to generate from present to the past. If you generate from past to present, you have to try to make sure that the properties of the past halo match the present, match that one halo that you were given at every time step. Yeah.
Thank you. Yeah, so with that, we're going to finish the first session. Let's thank Tree again. And